In this video and the following videos, we're going to take what we did in the previous video and formalize it into something known as phasor analysis. Recall we took our original voltage applied to the circuit, Vm cos omega t, and the first thing we did was we converted it into a form Vm e to the j omega t through adding an imaginary component and taking the Euler's form of it. And this allowed us then to relatively simply calculate that the current would be given by some magnitude times e to the j omega t, notice the frequency shows up again, plus some phase angle, which we call I. Then we took that form and we took the real component of it, and we could write that our current would be simply equal to the magnitude times the cosine of our radian frequency times time plus the angle that we analyzed. This greatly simplified our work. We would now like to formalize this procedure so that we can take advantage of these using what's known as the phasor transform. Before looking at the phasor transform itself, we have to figure out what is a phasor. Recall that any sinusoidal voltage is shown here or current shown here where the frequency is known is completely defined by its magnitude and its phase. Similarly, when we express it as a complex variable, as shown by the voltage here or the current here, if we know the frequency, then again the magnitude and the phase completely define the function. Indeed, we found in the previous analysis that the e to the j omega t term canceled out, and we were simply left with a magnitude and an angle or phase, and that resulted in our values, our variables are of the form x sub m e to the j times whatever that angle was that related to the variable. We can express that in an alternate form using Euler's identity as xm cosine of the angle plus j times xm sine of the angle. Since the form is known, we can simplify this and express it in a much more compact form simply as x is going to be equal to xm with an angle, where we simply specify the angle and the magnitude. This is known as a phasor. Usually, we use uppercase letters with a lowercase subscript to represent a phasor, and in many cases a bold font is also used. How do we get phasors? Well, we get them by using something known as the phasor transform, which sounds complicated but is really quite simple. Converting a variable, usually a voltage or a current, at a known frequency to its phasor form is known as the phasor transform. You'll note that the regular variable is a function of time, and so we call this the time domain. Later, when we write an equation using the phasor form, we find that they're typically only functions of frequency. Hence, the phasor form is often called either the phasor domain or the frequency domain. Converting a variable back to the time domain is known as the inverse phasor transform. While all this may sound complicated, the transform is simply a two-step process. The first step is to express any sinusoidal functions as cosine functions. Each function will have an amplitude and it will have a phase, and all the functions should have the same frequency. The next step to do the transform is the amplitude becomes the magnitude and the phase becomes the angle, or what we would write is that x of m cos omega t plus our angle transforms into a magnitude xm x sub m at angle x. This is our phasor transform, and the reverse operation is known as the inverse transform. Before going on to use the phasor transform, we have to answer two questions. The first question is, which circuit analysis techniques apply in the phasor domain? Fortunately, all the techniques that we've covered up till now will apply in the phasor domain. The second question is, how do we transform a circuit into the phasor domain? And we'll find that this answer is relatively easy. We will transform it element by element. And we'll proceed with answering these two questions in the following video.